Okay, this video is about enzyme active sites, and I've previously given the video before, but I've added something to it that I think is interesting. What I learned in, college and med school was basically you got two substrates for a reaction. An enzyme catalyzes it by stabilizing the transition states. It sort of holds the two reactants, the substrates, together in the proper orientation. So first of all, you need proximity to bring them together. Then you need correct orientation to put them in a position that they will react with each other, and the reaction occurs and you produce a product. It stabilizes the transition state. And we learned initially that there's a lock and a key fit of the substrate into the enzyme active site. Okay, so it has to fit just right, and so that the reaction can be catalyzed. And then we learned, oh no, to be more precise, we should say it's like putting a hand into a glove, and once the hand goes into the glove, it slightly changes the shape of the glove as well, and that's also called an induced fit. And this was, a progress step, and these are with, bright Stanford biologists, okay, talking about enzyme active sites. And, as a student, you just memorize what you have to learn. You're so busy, I didn't really think much. You don't start becoming creative till later when you know more. But anyways, here's an example of the substrates fitting into an enzyme active site, but it's not going to work in this case because they're not properly orientated to fit together. This enzyme active state, if you will, is too big for these substrates. Now here the substrates fit into this enzyme active site, and they're correctly orientated such that the green fits into the red, so to speak, and now the reaction can occur. In addition, to make a reaction occur, to attract the substrates into the active site, you can have a charged molecule. For example, here's a deprotonated carboxylic acid, and the negative charge will attract a positively charged substrate so that it can then undergo reaction. Let's say these were both positively charged. This might help attract them into this enzyme active site. And I'm building up something. I'm giving you the basics here. I'm going to show you something that I think is pretty interesting. I hope you're going to like it if you care about enzymes. Okay, and I was reading this book. I don't have it right in front of me, but the name of the book is called Oxygen, and it's by Nick Lane. Nick Lane is an English biochemist, and he's pretty good. I like him because he's very intelligent. He comes up with a lot of metaphors for describing, biochemistry and pathophysiology. He's part of the whole origin of life researcher group. And I did like his other book too, Transformer, where he's talking about Krebs cycle running backwards. Okay, so why am I talking about him? Because he talked about superoxide dismutase, like mitochondrial superoxide dismutase, the enzyme within the mitochondrial matrix in humans and other forms of life. And basically, it has an incredible speed of reaction. It speeds things up 1 billion-fold compared to how long it would take for superoxide to react and become like water, okay? And he described that not only do you have an attractive charge in the center of the enzyme active site, but you have a whole series of electrostatic guiding charges. It's like a plane landing with the runway lights. They guide the substrate into the enzyme active site. This is a rather beautiful metaphor. All the great scientists are a little bit artistic and creative. That's what makes them great. Like Douglas Kell talks about iron behaving badly. It's brilliant. All right, so anyways, I just thought it was such a beautiful metaphor. I'm driving my car. It was an AO, academic orgasm. It was so beautiful, his conception of how enzyme active site works. And it's also, in retrospect, you go, that's obvious. Of course it does. Well, you know what? It wasn't obvious. No one else said it, okay? And most of the time you don't think about it. That brilliant mind thinks about something and figures it out, although it sounds obvious. So I'll give Nick Lane credit. He came up with a beautiful metaphor here, and he's come up with a lot of other great metaphors, and that's why I read his books, even though he goes through all this long-winded stuff about the origin of life. And I actually think James Tour is better than him on origin of life, but Nick Lane still has taught me some good things, so I like him. So anyways, this is the airplane. Those are the runway lights, and you're going to see in a moment, I have a drawing how this is like an enzyme. Oh, and by the way, here's my own metaphor, is that it's like a vacuum. Wait till you see this enzyme drawing, how it sucks the substrate, the reactants, into its active site. I thought it was pretty cool. So here is the first metaphor of the charged reactants in the enzyme active site being like a magnet to pull I just drew like these metal balls, if you will, to be pulled into the active site. And yeah, that's great, but in reality, the enzyme is kind of this giant thing, and like less than 1% of the enzyme's shape is its active site. So if they were to just randomly collide with the enzyme, most of the time it would be bouncing off the sidewalls, completely irrelevant to causing the reaction to occur. So the point was, what Nick Lane meant by the runway lights was you have positively charged molecules. For example, lysine is a classic positively charged molecule, and it's one of the molecules that contributes to the guidance system to get the oxygen. It's actually a superoxide anion, negatively charged, to be sucked into the active site. Inside the active site, this is mitochondrial superoxide dismutase. Inside the active site, you got a manganese 2+ charge. That's sort of like winning the prize, okay? All right, so anyways, the superoxide anion is like sucked in there. That's what I meant. It's like a vacuum cleaner. So fast, it'll suck it in there, pop it out. Suck it in there, pop it out. I mean, it's incredible how fast all of this occurs. So anyways, this idea of runway lights being like guiding a plane to land, I thought that was really kind of neat. Okay, I'll show you another thing about enzyme active sites. One more slide. The next slide coming after this is pretty good too. Okay, so this is what it does. For a reaction to occur without the enzyme there, there's such an unfavorable energy quite often to produce a transition state that it doesn't get done. Versus with the enzyme, it lowers the transition intermediate energy level such that it's much more able to rapidly catalyze the reaction. So that's one of the things that an enzyme will do. Okay, now here's something where it gets interesting. There's a lot of pathogens that mimic normal stuff. So here's glycine, the smallest amino acid. So an amino acid has an alpha carbon, and I think it looks like a Christian cross, okay? And the reason I say that is the center of the cross, the chest of the cross is right here. The head's like the hydrogen sticking up. The R group is what sticks down, a variable length. And then there's always off to one side of the cross, if you will, a carboxylic acid on one side and then a amino group on the other. That's why it's called amino acid. Here's an amino and here's an acid. So it's an amino acid. Okay, and glycine in particular just has a hydrogen as its side group. It's R group. And the unique thing about glyphosate, the herbicide, is that it's just like glycine, but it has this additional phosphate on it. There's a little more than a phosphate, but you can think of it as being a phosphate. All right, and in some cases it can substitute for glycine within molecules, and that ends up being a very big deal. The person who's written the most about this is Stephanie Seneff. So here's an example of a Trojan horse. Of course, that's from the Trojan War, where the Greeks were fighting the Trojans, and Odysseus had the idea, and they climbed inside the horse at night, and then they left it as a gift to the Trojans, and the prophet of Troy said, no, don't let it come in, but the people were stupid and they let it in. Okay, and it turned out to be a big problem. All right, so now I'm going to show you how that relates to enzyme active sites. So here might be the normal enzyme active site with just like an alanine, a small side group there, and then glycine, a really small side group. You'll a lot of times have glycines around an enzyme active site or pocket because it's such a small side chain that creates more space to let the reactants get in there. And the point I'm making is instead of having a glycine there with this tiny little hydrogen side chain, you can get a glyphosate in there. And you can see how this is going to mess up the enzyme's active site because now you put a negative charge in there where you don't want one. Plus the phosphate is rather big and bulky. So it's going to prevent the reactants from effectively coming into the active site. And again, Stephanie Seneff, PhD from MIT, has written a lot about this. It's on page 57 and 58 of her book, Toxic Legacy. And so this is a glycine glyphosate substitution for glycine. And you can see how this could decrease that enzyme's function. Okay, and she makes the point that, in her opinion, based on her extensive research, there is a lot of examples where glycine is doing, or glyphosate is doing something like this, mimicking glycine's effect in the body. So that's rather interesting. So anyways, this was just to show you how this can happen. This is another reason why I think it's important. You know, if you've got the option, try not to eat anything sprayed with this glyphosate, okay? So anyways, I thought that was interesting, especially that stuff about being like the runway lights to guide a plane to land, to guide the substrate into the enzyme active site so rapidly that it happens 1 billion times faster than it normally would. It's kind of, I thought that was kind of neat.